So if you want to contact me later, I encourage you to do that, because I have found that usually you have questions that occur later, 1 month, 1 year, or so on, and I'm always happy to take some time to help people. So please feel free to contact me whenever it is that you like. But we should start off with, when is multiaxial fatigue important? And there are really two problems. The first one is that we have a very complex state of stress. And the second one is that maybe we have a simple state of stress but a complex loading pattern. And throughout the next few days I want to look at both of those problems. And I want to start with a little bit of nomenclature and to also see if you are paying attention. And so, of course, we talk about a uniaxial state of stress, and almost all of our knowledge is built up from this test case. And so we have bars that look like this, or sheets that look like this, and we load them in only one direction, uniaxial loading. If we think about this in three-dimensional space, then there's one positive principal stress. And then we talk about the term proportional loading or proportional biaxial loading, and this is a case where all of the principal stresses in any coordinate system you like are related to one another, right? And I just write that it's by some proportionality constants always. And this is what would happen if I twisted the bar. Right? So if I took this bar and I twisted the bar, then one principal stress would be positive, one would be negative, but they would always be in the same ratio, no matter how I change the loads. And then, of course, you can have some arbitrary path. For example, I load this and I pull this and I twist this and I pull it and twist it at the same time. So I like to give examinations and quizzes throughout the class. So this is the first quiz, right? I have this bar. Right? And I load this bar in tension, like this, right? And then I load this bar in compression, okay? Is this uniaxial loading? I just take this simple bar, I load it in tension, and then I push it in compression. What kind of loading?
Uniaxial.
Uniaxial, right? How many agree? It's okay if you don't, right? How many are sleeping after lunch? This is always a possibility. Uniaxial, right? Well, pushing this in tension, pulling this in tension, and pushing this in compression is uniaxial to anyone who's ever been in the laboratory, because it's loaded only along one axis. Okay? But this is actually non-proportional loading from the mathematical viewpoint. And I tell you this to be careful of the math. Why is this, right? So remember, the principal stress, the order of the principal stresses is the largest principal stress is first, sigma 1. Then the middle. The smallest principal stress is sigma 3. So when I pull on this bar, right, sigma 1 is in this direction. And has a magnitude whatever the stress is in this direction. Okay? When I push on the bar, sigma 1 is in this direction and is magnitude 0. So the first principal stress is changed from this direction to this direction. So it's a non-proportional loading. And this is the problem with people who only look at the math. If you only look at the equations, right, then, oh, this is a very non-proportional case. Principal stress direction changes from this direction to this direction. Okay? But if you ask anybody who's been in the lab, oh, this is a simple uniaxial loading. And this is a lot of the problem with the different multiaxial fatigue theories. Right? The people have developed this only from the mathematical perspective. And you run into these problems. And sometimes you get answers which make no sense. Absolutely no sense. And so I want to talk a lot about what happens in fatigue and how it happens. Just like you all know that if I pull and push this, it's simple uniaxial loading. Okay. So here's the real problem. So there's a crankshaft from an engine. And here are the loads that exist on that. And you can see measuring what the strains are. Sometimes all of the loads are in phase, and sometimes they are out of phase, and sometimes one is in phase and the other not, and so on. And to be honest, I find these kinds of plots very confusing. They tell me nothing, right? Why do they tell me nothing? Well, right, material doesn't know a lot about the external loads. The material knows what happens in certain directions. So if I take those loads and I think about applying those loads out here someplace, whatever they are, in tension and torsion and bending, right? A little element of the material understands the stresses and strains that act on that element. And we can look at the stresses and strains in different directions. So first we look on the surface, and if we look at the tension strain and tension, and we can look at the shear strain like that, and we look at a plane that looks like this at 0 degrees, then we see behavior that looks like that. And when you look at it in this plane, then you can see this crankshaft sees a lot of bending loads like this, and it also sees sometimes when it has twisting and bending together. Right? Never pure twisting. Right? But you know, if I do an experiment, right, and I apply those loads to the end of this bar, I have no idea where this will fail. Maybe it will fail in this direction, maybe not. So I have to check other directions. Right? So I say, okay, what happens in this direction, 90 degrees? And so you get behavior that looks like this. And you can look at 45 degrees. Right? What happens on a plane like this, right, in the material? And at this direction, 45 degrees, right? All plots at the same scale, then you can tell with your eye, this must be very damaging. Look, big cycle in tension, right? And many shear cycles. Okay? And if I look at the other plane, right, almost nothing, right? So where would you expect this to fail? Sure, in the place with the biggest strains. Right? You would never know this from the original loads. You would only know this after you start to think about what are the stresses and strains that act on different material elements. Okay? That's the whole secret of multiaxial fatigue. Nothing else is needed. These two ideas, right? First one I gave you, right? The math is wrong about the principal stresses. Most people do not really understand about the state of stress. And the second one is most people don't understand how forces combine to produce fatigue damage in certain directions in the material. Right? Those are the two main points. Now, right, since you've all come from a long ways, I feel I have to elaborate a little bit. But those are the central ideas. Right? Those two. Okay, there's another problem where multiaxial fatigue is important, and that's where you get the complex state of stress. And so I just take a bar like this, right, plate, 100 millimeters wide, and I put a 25 millimeter hole in the center of this plate, and then I measure the strains, and I can measure the strain in the X direction, the tension strain from pulling on this plate. And I can also measure the transverse strains in the Z direction. And what you do, okay, so here's a plot of those two. And if I make a very thin plate, right, then I get behavior that looks looks like this. And of course, this slope is 1/3 the elastic Poisson's ratio. And after it starts to plastically deform, then this slope is 1/2 the plastic Poisson's ratio. But if I make the plate thicker, same dimensions. Of course, if I make the plate thicker, then I have to apply more force. But to get the same tension strain, you can see that as I make the plate thicker, then the amount of strain, transverse strain, becomes lower and lower and lower and lower. Okay? So if I did a fatigue test of this plate in the different thicknesses, and I based the fatigue assessment on the tension strain, right, then the analysis would show all plates have the same fatigue life, even if it's thicker. How about the experiments? Same, everything the same, right? Same nominal stress. Right? Does a thick plate have the same fatigue life as a thin plate? How many think the same? No one. How many think longer? No one. A few. How many think shorter? Why do you think it's shorter?
Because the probability that there are more failure in the material is higher.
Yeah, that is true. There's more material, so it could fail. Right? There's a second reason. Right? The stresses are actually much higher in a thicker plate. Sure. Right? Here are the stresses which are built up. Because the thicker plate prevents the transverse contraction, and so it's in a state of plane strain, and so the stresses will be higher by about 1/4. And you find in the test, the thicker plates always fail first. In the thicker plates, the cracks always start in the middle, where the stresses are the highest. So this is a multi-axial fatigue problem, even though the geometry is very, very simple. So the only true uniaxial fatigue problems come for situations of very thin structures in plane stress. Everything else has three-dimensional stresses that are built up. Everything else. Okay, so that's a background of where we will be. And I told you I will fill in some of the details. And so I have prepared 8 different topics. But I will not cover I will cover the topics in order, but each topic will not take one lecture. Some topics will take more than one 2-hour period, and other topics less, such that we will end at the appropriate time. So, I always like to start off with the history, because I think it's important to see what other people have done. And I like to talk about the early history of fatigue in the first 100 years, and to take a few minutes to do that. And you know, a lot of the work in fatigue was done in the 19th century. And our understanding of the fatigue process was actually well developed by the beginning of the 20th century. And so what I would like to do in the next few minutes is just to show you a few of these things and the key ideas that came, and to remember the year that the key ideas came, and you can think about, based on your own experience, how much progress we have made over this time. So the first fatigue in the literature actually comes from the French, about the idea of fatigue. And it is translated literally from the medical term fatigue. The people at that time believed that materials got tired and worn out, just like you get tired and worn out after working some days. And there have been many famous accidents. This is one of the earliest that's in the newspapers. And It's from a train. 1950. So the people from Paris went to Versailles, spent the day drinking, I suppose, and then at the end of the day, then they have to take the train back to Paris, and unfortunately this train had an accident. And in the train, they had a lot of passengers. I let you read this on your own. So this is from the London Times. Right? I suppose that's something that's very common here in Europe, which we don't find so much in America, in that the Europeans like to make fun of the other countries. And so on. We never do that in America. Right? We make fun of whole regions. I live in the north. Right? It's fun that we make fun of the people who live in the east or the south or the west, but you know we're normal in it. Anyway, so they had this failure, and unfortunately, they had a long train, right? So you can see the number of passengers, and this is one of the stops between Versailles and Paris. There were 2 engines on this train, and the axle of the first engine broke. And the second engine passed over it and the boiler burst. So you can imagine that this is very detrimental. And unfortunately, 6 of the cars caught on fire. Okay. And then 3 were consumed without the possibility of escape to the unhappy inmates who were locked up. So can you imagine this today? If you got on a train and they locked the cars from the outside. So no possibility of emergency exit. None. All of these cars were locked from the outside to prevent people from leaving the train. Yeah. So there has been progress. There has been progress in safety. And unfortunately, many people were killed. And this is a fatigue problem. And there's an early steam engine, and in the not an engine. Okay, there's what an axle looked like in it, and so there was a step shaft, so you could have a wheel and also a bearing. And if you read through this accident, then you will see where they forbid the use of the second engine. They forbid the use because it was improperly designed. So, we look at the axle a minute, right? So this was the traditional design. So there's an axle, and maybe we have a wheel. And a bearing. Okay. So that was the normal design. And the one that failed looked like this. Bearings on the inside. Optimization of material, I suppose, right? Because the axle is shorter. This one. What's the difference in the stresses in the axle from these 2 designs? Because remember, in 1850, this is before very much strength of materials. So there was no concept in 1850 when this was designed about calculating bending stresses and strength of materials, and no concept of stress concentration factor. Concept of stress concentration factors and stress concentrations did not come until 1910. We think these things have always been known. So what's the difference between these 2? Which one has the highest stresses? Remember, I can wait a long time because I enjoy listening to the music and I can tolerate silence. Very interesting. So I spend at least 1 month and sometimes 2 months in Japan every year these days, and I like to do some teaching there. And sometimes I have to wait forever, because all of those things you have read about the stereotypes of the Japanese professor are true. The Japanese professor comes in and spends all the time talking to the blackboard and then leaves. And then after the professor leaves, then the graduate students come in and explain what the professor was supposed to have said. So unfortunately, I have no graduate students here, so you're stuck with me. You're just stuck with me. But I try not to speak to the board. All right, what's different about these two from a stress perspective? Yes.
Fraction is applied to wheels.
Yes. Yeah. Yeah. So the reason you're having trouble is you can't find a difference, and that's true. Right? So if we look at these two designs, and we think about I have the force up on the wheel and the force like that, and here I have a force down from the weight of the vehicle, right? Then all of the stresses are determined by the bending moment, and the bending moment is determined only by these forces and what the spacing is. So if this spacing is the same, then of course all the stresses are the same, because it's in simple bending on both ends of the beam. So there's absolutely no difference. But you know, they didn't know that in these days, and what they did was they simply banned this engine, because obviously it was designed wrong. Obviously it was designed wrong. You know, that's something that still happens today. If there's an accident here or in any other country, then the political people feel the need to do something. And they do something, not necessarily based on fact. And that's what they did. They just banned the use of this engine, right? Took all the money from the company that made it, and so on. So it's been, these things have been going on for a very long time. Next thing I'd like to talk about was the expert opinions of the time. I encourage you to read the old literature. And the old literature is very different from today. So if you want to publish a paper today, then you do some good research work, you write a paper and you write the ideal paper. Okay, ideal paper should be 6 pages, 10 figures, right? Few conclusions, right? Make it appear that you almost solved the problem, but not quite, so it's possible to get some more research funding. And okay, we go on. If you go back to this time, then the papers were actually, somebody wrote down everything that was said. And so people would come to a meeting, and someone would make a presentation, and they would have their charts and pictures and so on. And somebody would write down exactly what was said, and then people would ask questions, and all the questions would be part of the paper. So they would say, you know, Professor Barthwaite presented so on and so on, and Mr. So-and-so questioned this, and if it was a very vigorous discussion, then they wrote that, and you got that in all of the discussion. And so this is what they wrote about those problems. Okay. I never met one which did not present a crystallization fracture. So the early people studying about fatigue thought that fracture occurred because the material crystallized. What does that mean? If you have a piece of good material and you do a tension test and you look at the fracture surface, then the fracture surface is very irregular. And so it looks like if you pulled apart this good material that it was more like fracture of a piece of wood. Okay? And then you look at a fatigue fracture of the same material. And of course a fatigue fracture is very flat across, very much like the fracture of a rock. And so they thought that somehow all of the materials mysteriously crystallized. And after they crystallized, then they broke. That there was some material transformation. We know, of course, that's wrong. Right? But it doesn't stop people. If it happens, you need a reason for it happening. Okay? Now, it's not a surprise that almost all the failures happened in the locomotive part. So it must have been caused by steam and heat and somehow magnetism. I don't know. Well, you know, of course it's going to be in the locomotive because it sees the highest stresses. It's the biggest, right? It does have all of this heat, so that must have been the reason that caused this crystallization. And the other thing is, right, the change may take place instantaneously. The train was rolling down the tracks, and all of a sudden the wheel fell off. So that was an instantaneous change. Okay? And then they thought steam must have had something to do with it, because that speedily caused the iron to become magnetic. So these were the early opinions, right? Absolutely wrong. Of course. Absolutely wrong. So next time your professor tells you something you don't believe, it's okay to say the expert is wrong. Right? These were all experts. Right? My students have done this to me frequently. Frequently I have been wrong. Okay. But, you know, you have a good professor. They do know the answer. And this is Rankine. And he was trained as a civil engineer. And you recognize this Rankine maybe from thermodynamics. But his first two papers were in fatigue. Not in thermodynamics, for which he became very famous. And unlike the others, right? Rankine did some observation and simple experiments to show him what happened. And he said, the deterioration of the axis is always gradual. The wheel falling off at the end is the result of a long process. And here is his description. The fracture started with a smooth, regularly formed fissure, literally translation from the French for crack, extending all the way around the neck of the journal, rotating, bending fatigue as it goes down the track, until it reached an average depth of about 1/2 inch. He looked at the fracture surfaces to see. And then the thickness of sound iron in the middle was insufficient to support the shock loads to which it was exposed. Pretty good description. Even today, right, if you were to write the description of a fatigue failure, right, this is it. The only thing he didn't know was he did not have any idea about our modern concepts of fracture mechanics and the importance of the crack, other than to know it was there and it grew slowly. But you know, if you have someone who's really knowledgeable, right, they tell you what to do. Not only why it happened, but what to do. And in his second paper, he said, you know, I just looked at the rest of the specimen. It seems easy enough to do, doesn't it? If I thought there was a crystallization of the material of this specimen, why not look next to the failure and see if the iron remained fibrous? And that's exactly what he did. So he looked and said, oh, there are no changes in the material. And then he said, you know, the fracture always occurs at the sharp corner of that journal. He said, just make it bigger and we'll be okay. 50 years before the concepts of stress concentration. 50 years. So, you know, the fatigue problem and its solution was laid out 150 years ago. Pay attention to the shock loads and pay attention to the local radiuses. Same advice you would give today. Pay attention to the local radius. Pay attention to the shock loads. The next part of all of this is Wohler, German. He worked for the railway, and his work was all done before the advent of the microscope, so he could never see what happened. And he searched for a critical value below which failure would not occur. So there's his testing machine, and so he tested bars and bending powered by a steam engine. If you look at Wohler's tests from 1850, in 150 years, we have managed to replace the steam engine with an electric motor. But the test is the same as from Wohler. So those of you who are knowledgeable in the fatigue literature will know about the Wohler curve. Yeah. How many know about the Wohler curve? Everybody, right? Fine. Did you know that Wohler never plotted his data? Voller never drew a Voller curve. Never. No, this is afterwards. Voller, right, was studying fatigue, but this is not what Voller liked to do. Voller liked to build equipment. And so if you read Voller's papers, right, so his papers may be 20 pages long. The first 18 pages are a very elaborate description of the test machine, how it worked, and all of these details of the test. And then on the back, there's a table of the data. And that's all. Right? Never a curve. Never a curve. Yeah, that came much, much later. Much, much later. So I'm like Voller. I had to publish some papers, but I was always more interested in being in the lab, building machines, and to see what happens. Much more so than the paper publishing.